All right. Let's take a look at Unit C1 example, page 9. Bernoulli's equation. So let's apply Bernoulli's equation for this particular case. Let's consider the flow of air around a bicyclist moving through still air with velocity v0. It's shown in the figure. Determine the difference in the pressure between point 1 and point 2. Point 2 is right here, forehead of this bicyclist. Something called stagnation point. All right, so let's take a look at the picture here. This is massively, simplified bicyclist. Okay. So, well, camera passes nothing. So, but anyway, so this is, I guess you can understand. This is bicyclist, massively simplified, schematic. Okay. So what I wanted to emphasize here is, it's fairly confusing if you take a look at this figure. There's a problem on this figure. Okay. Let's just take a look at once again the problem statement. Problem statement says that this bicyclist is moving through still air. That means air is actually not moving. Okay. Velocity is v0. That's the velocity of this person moving. Okay. Then determine the points 1 and 2. Now, point 1, as you can see, v1 equal to v0. Wait a minute. Point 1 is right here. It's a still air. Air is not moving. But it says velocity is v1 equal to v0. Oh, what do you mean by that? v2 is 0. Velocity is here? 0. Why it's 0? This person is moving. So this is, relatively speaking, fairly confusing. So I wanted to draw two figures here to emphasize what it really means to have a difference between actual situation versus equivalent situation. Almost. This is an equivalent situation. What is the equivalent situation we always create in order to test flow around some kind of moving object vehicle, typically airplanes? This is a wind tunnel, right? So this is actually a very good example program in order to introduce you the concept of wind tunnel testing. Okay. Now, oftentimes we have a wrong idea that wind tunnel exactly represents the actual situation, which is not true. Wind tunnel only represent equivalent situation. We're going to talk about that later, why it's only equivalent, it's not actual. First of all, the purpose of the wind tunnel is the change of point of view. In other words, coordinate system is different. This person is moving within non-moving air. We recognize this person is moving based on the coordinate system attached to non-moving Earth. Okay? So, what is the velocity here? Velocity is everywhere 0. Velocity is everywhere 0. Velocity of this person is v0. That's the situation. However, we can pick up this person, let's imagine bicyclist. Let's pick up that bicyclist and strap into the wind tunnel test section, and then turn on the wind tunnel fan on. Then air starts blowing. I'm not kidding. I actually one of those days when I was a graduate student, one of the research project was to design the best helmet, aerodynamically speaking. So we picked up an actual person with a different kind of helmet with a bicycle, stick into the wind tunnel, then tested the drags to find out what kind of shape of filament minimize the drag. So it's one of those actual projects. So this is a situation. So bicyclist is placed in a wind tunnel. Obviously this person is not moving at all. It's just stuck there. Okay? Then you turn on the wind tunnel, the air starts blowing. Supposed to be, if you represent the equivalent situation, air speed within the wind tunnel must be exactly equal to this v0, which is a person moving. in the still air. Is that right? So this B0 is wind tunnel's test section airspeed, something called free stream. In aerodynamics, we are going to oftentimes use the B infinity to represent free stream. This infinity really means that this is the move of air infinitely forward of this model. So this is undisturbed air, which is completely not affected by the presence of the model. So this is called free stream. So infinity means, ideally speaking, this is the free stream velocity B0, which is completely undisturbed by the presence of this model. Free stream. Okay. So in this particular case, free stream is B0, which is the same speed as if this person is moving in non-moving air. Okay. So this is wind tunnel test. So let's go back to this figure once again. So this problem is essentially talking about as if this person is in the wind tunnel. Velocity here is B0, which is B1, which is speed that person is moving. Okay. Right here, let's go back here. If the air is moving towards you, you are not moving, then let's determine one of the streamlines that goes right into your head. Burn. So velocity right here, let's call this location 1. Velocity right here, location 1, is essentially equal to B0, which is oftentimes B infinity, called free stream of the wind tunnel testing. Okay? So if you pick up a small tiny particle of air which is moving along this free stream, so the particle starts from really far away, slowly picking up the speed and sucked into the wind tunnel, and then accelerated to velocity B1 here, and then bang, hit the face of this person, stops to 0. Okay. So this is a location 2. Location 2, velocity is 0. In other words, this is called stagnation point. Okay. So that's the pressure you feel if you pick up a bicycle and ride on it and pick up a really fast speed going down the hill. You feel the pressure pushing you backwards. Okay? Why is that? Because you're creating the stagnation point, so velocity rises up. Well, no, velocity goes to 0. Pressure rises up because of that. Why is that? Bernoulli equation. Right? Bernoulli equation says, well, let's apply Bernoulli equation for this particular case. So let's apply Bernoulli equation. Along a streamer, which is this particular stream, right? Between location 1 and 2. So you can say P1 plus 1/2 rho B1 squared is equal to, actually, plus gamma Z1 is equal to P2 plus 1/2 rho B2 squared plus gamma Z2. By the way, this is Z2, this is Z1, it's about the same, so you can drop off this term. Or you can argue about it. This is air. Gamma air is so small value, so approximately 0 also. Okay? So you can have both arguments. If this is a water flow If height is the same, there's no difference. If this is airflow, usually we just ignore the hydrostatic pressure difference within air. Anyways, so this equation actually leads you to the fact that because the B2 is 0, we can say P1 plus 1/2 rho B1 squared is equal to P2. So right here, pressure is P1. Right here, is pressure is P2. P2 is much higher pressure than P1. How much higher? This much higher. Because you're moving, you're going to add dynamic pressure component. So if you move faster and faster and faster, you're going to keep adding bigger and bigger and bigger value. So ended up having higher pressure developed right here. So when you go faster and faster on your bicycle, you feel more and more and more high pressure at your stagnation point. Okay? So that's what it is. So the problem is asking you, okay, so what is the pressure difference between point 1 and 2? Pressure difference is this, right? But anyway, pressure difference, delta P, which is equal to P2 minus P1, is essentially this, 1/2 rho B1 squared. What is this? This is called Q, dynamic pressure. Okay. So is there any way to actually measure this? Can we measure pressure difference using some kind of device? I guess we can. If so, if you know the density of air, you can determine B1. What is B1? B1 is how fast you're moving. This is called airspeed. If it's airplane. If it's bike, it's a bike speed. But anyway, the speed you are moving can be determined by measuring the pressure difference between free stream and stagnation point and knowing the density of air itself. Okay? So later on we are going to find out how to determine airspeed. We do have a device called Pitot-Static Probe, combined with some kind of device that actually can determine pressure difference between two pressure sources. What is that? U-tube differential. Sometimes inclined. Inclined is actually better because delta P is very small value. Manometers. So the combination of this will determine airspeed of vehicles, how fast moving, how fast this vehicle is moving. It's called airspeed. If this is airplane, you can determine airspeed. Even if this is bicycle, you can determine how fast you're moving. Okay? Maybe just to show you a Unit B3, just a very vast page. Okay. So this is the Pitot-Static Probe. We looked at it in Unit B3 combined with inclined U-tube differential manometer. Okay. So this device measures two things. Pressure in the center tube. Now keep that in mind. This place is a stagnation point. You know, compared against the bicyclist, that's the pressure you feel right here, highest pressure, stagnation point. Because air particle move in along this streamline, burn, hit to zero. So this is stagnation point, determines something called total pressure. Side port of this tube measures the static pressure. So if you take a difference between total pressure and static pressure, you can determine that using this device. It is dynamic pressure. Once you determine dynamic pressure, you can determine airspeed of this flow. So this is one of the ways you can determine airspeed of the wind tunnel test section. You can use the exact same concept applied for airplane. Pitot-Static tube determines airplane's airspeed. Okay. So it all comes up here. So once again, let's just take a closer look at Bernoulli's equation. Bernoulli's equation tells you really tells you static pressure plus dynamic pressure is equal to total pressure. M means gamma of air is approximately 0. So obviously gamma times z term is completely dropped off. So this is a static pressure. This is total pressure. Total pressure can be measured at the stagnation point. Okay. So what this device does is going to determine pressure difference between this port and that port, this port and that port. So the reading of this device in terms of typically inches, that inches of reading is essentially pressure difference between static and total pressure, which is called dynamic. So when you walk into the wind tunnel, and if you ask somebody how fast this wind tunnel can go, the typical answer is, well, 5 inches of water. What do you mean by that? Well, that's how much dynamic pressure head you can produce by turning on this fan to the maximum speed, which is converted into how much inches of water rise up in this manometer. Actually, not the manometer, it's vertical pipe. It's a pressure head. So that's the expression of dynamic pressure head you can produce for a given wind tunnel testing. It is all coming from this Bernoulli's equation. So it's very, very important fundamental equation to understand how the airspeed is determined. Okay. So we are going to take a look at more about Bernoulli's equation, but hopefully you need to understand very, very basic concept about Bernoulli's